Welcome back to educator.com. Today we're going to finish up our study of fluids by talking about Bernoulli's principle. Our objectives are going to be to understand how Bernoulli's principle describes the conservation of energy in fluid flow and apply Bernoulli's principle to problems of fluids in motion. So let's start by talking about Bernoulli's principle qualitatively. Bernoulli's principle states that fluids moving at higher velocities lead to lower pressures, and fluids moving at lower velocities lead to higher pressures. This comes into play quite a bit when you talk about the design of an airplane wing. If the airplane's moving forward to the right, then as the air goes over the wing, it has a longer path up above the wing. Because it has a longer path, compared to below the wing, where it has a shorter path, above the wing with the longer path, it has a higher relative velocity. If you've got the higher air velocity over that wing, you get lower pressure. Where you have the shorter path, you end up with a lower velocity. The air doesn't have to travel as far in the same amount of time, so you end up with the higher pressure. If you have higher pressure below and lower pressure above, that wants to equal out, and you get a net force up. That force is one of the components of lift. Now note that it's not the only component, that there's a lot more to lift and flight than just Bernoulli's principle in the airplane wing shape, but that's one component of it. One application of Bernoulli's principle. Another one is called a Venturi pump. The idea here is that you can make a vacuum pump or another type of pump using fluid flow. If you have fluid, an incompressible fluid in a closed system coming through from the left to the right here, and as it goes there you have a narrowed opening, you must have faster flow here. We know that from our continuity equation for fluids. And if we have faster flow, we must have lower pressures here. As we have lower pressures there, what we're going to get is a pumping action in which we can start sucking things up this way to join that fluid flow. So force a lot of water or some other fluid through the pipe this way, constrict it here, and you're going to get a sucking action. You're going to get a pumping action. These are used in Venturi pumps, applications of those, things like carburetors. It's responsible for sailboat propulsion, gas delivery systems, or even for some folks who have basements with sump pumps in case the power ever goes out. Oftentimes you'll see these as a backup sump pump. When the power goes out, if the water level gets too high in the sump, what happens is it lifts a float that turns on a bunch of water pressure. The water pressure comes running through here, and this is connected to that cistern and sucks up the water to pull it out with that pumping action. A way to help keep your basement dry even when you don't have power to keep that sump pump running. All right, Bernoulli's equation quantitatively looks a little bit scarier. It relates the pressure, velocity, and height of a liquid in a tube at various points. Don't let it scare you. It's all a fairly simple equation. It just looks like a lot all at once. Pressure 1 plus 1/2 the fluid density times the square of its velocity plus the fluid density times g times its height equals P2 plus 1/2 rho V2 squared plus rho GY2 squared. Really what this is a statement of conservation of energy. Notice how similar this looks. 1/2 rho V squared to 1/2 mv squared, similar to kinetic energy. Rho gy, similar to mgh, similar to gravitational potential energy. Some pretty close parallels here. It really is a version of conservation of energy. What it says is the pressure at any point in the tube plus half the density times the square of the velocity added to rho gy must be the same anywhere at any point in a tube. So, as we check this out, let's take a look and use it to derive what's known as Torricelli's theorem. If we have water sitting in a large jug at a height of 0.2 meters above the spigot, what is the pressure on the spigot? And with what velocity will the water leave the spigot when the spigot is opened? Well, the first thing we need to realize is P1 up here and P2 up here are both open to atmosphere. So we're going to say P1 equals P2 is equal to atmosphere. And we're not going to worry about the difference in height compared to the overall atmospheric pressure. That's going to be negligible. Now, as we start to look at this, we'll start by writing down Bernoulli's theorem. P1, or Bernoulli's equation, P1 plus 1/2 rho V1 squared plus rho GY1 must equal P2 plus 1/2 rho V2 squared plus rho GY2. Now, as we look at this, up here at the top of our fluid, because we have so much fluid there, we can assume that V1 is approximately equal to 0. Okay, now, pressure 1 and pressure 2 are both atmosphere, so we can subtract both of those right out. That'll simplify right there. We said V1 is approximately 0. That term goes away. So what we're left with now is rho GY1 equals 1/2 rho V2 squared plus rho GY2. All right, we're getting closer already. I can divide out the density to say that GY1 equals 1/2 V2 squared plus GY2. Or solving for V2, V2 squared is going to be equal to 2G times the quantity Y1 minus Y2, which will be 2 times 10, and our height difference from Y1 to Y2 is just 0.2 meters. So that implies that V2 squared is going to be equal to 4, or take the square root, V2 must equal 2 meters per second. And what we've really done here is we've derived what's known as Torricelli's theorem. This part right here, V2 squared equals 2G Y1 minus Y2. Or, more commonly written, take the square root, V2 is equal to 2G times Y1 minus Y2 square root. Calculating the velocity coming out of a container of liquid like this. Torricelli's theorem. We could look at an example with gauge pressure here too. Water flows through a large diameter pipe at point A before it's constricted into a smaller diameter pipe at point B. How does the gauge pressure compare at points A and B? Well, if the water is going through this pipe and it's being constricted, it must be going faster, right? So the velocity at B must be greater than the velocity of A. We know that from our continuity equation for fluids. If it's going faster at B, then B must have lower pressure than A. Therefore, A must have a higher pressure than B. Let's take a look at the shower problem. A water main of area 0.003 square meters at ground level flows at 2 meters per second into Kate's house. At the second floor shower head, 5 meters above ground level, the pipe has an area of 0.001 square meter. Find the velocity of the water in the pipe, as well as the gauge pressure just prior to the shower head, if the water main's pressure gauge reads 2 atmosphere. Well, let's start with the diagram here. Water main of area 0.003. So we're going to start over here with the pipe over here at ground level, and we know if we put a gauge on it that it's going to read 2 atmospheres right there. And it's got a cross-sectional area of 0.003 square meters, and it's flowing at 2 meters per second into the house. That's at section 1. Now, somewhere up here, it has a height difference of about 5 meters, and before it comes out, it is now down to a cross-sectional area of 0.001 square meter. We need to figure out here at section 2, area 2, what the velocity is of the water in the pipe, as well as the gauge pressure just prior to that shower head. To start off, to find the velocity of the pipe, I'm going to use the continuity equation for fluids. A1 V1 equals A2 V2. Therefore, the velocity here at point 2 is going to be equal to A1 over A2 times V1 or 0.003 over 0.001 times V1, which was 2 meters per second, or 3 times 2 will be 6 meters per second. All right, now let's see if we can find out the gauge pressure just prior to that shower head. All right, we'll use Bernoulli's equation, P1 plus 1/2 rho V1 squared plus rho GY1 must equal P2 plus 1/2 rho V2 squared plus rho GY2. Now, if we set Y1 over here and call this ground level, Y1 is 0, that term becomes 0, that goes away. And now let's start substituting in our values to see if we can't find what P2 is going to be. Over here at P1, we already know our pressure is 2 atmospheres, or 200,000 pascals, plus 1/2 times the density of fresh water, 1,000 kilograms per meter cubed. V1 is 2 meters per second. We're going to square that, plus, oops, we already got rid of that term, so that's going to be equal to P2 plus 1/2, our density again, 1,000, V2 squared, that's going to be 6 meters per second squared, plus rho 1,000 times G, 10, and Y2 is 5 meters higher, so 5. So a little bit of math here. 200,000 plus 1,000 times 4, half of that, that'll be 2,000, equals P2 plus, that's 36,000 times 1/2, 18,000, plus 10,000 times 5, 50,000. So solving for P2 then, I find that P2 must equal 202,000 minus 68,000, or 134,000 pascals, or approximately 1.34 atmospheres. Great. Let's take a look at a water fountain example. Sandy is designing a water fountain for her front yard. She would like the fountain to spray to a height of 10 meters. That's a pretty impressive water fountain. What gauge pressure must her water pump develop? Well, let's start with the diagram again. We'll start over here at her pump, and that's going to go to a point where it's going to release the water up at ground level. And once it's there, we want the water to go up to a height of 10 meters or so. So we'll start again with Bernoulli's equation. P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. If we call this section over here on the left 1 and over here 2, right away we can make some simplifications. At 1, we will assume that we have so much water, the velocity there in the pipe is roughly 0. That term goes away. We're also doing this at ground level, so Y1 is 0. On the right-hand side, at its highest point right here, we want the velocity of the water to be 0. That's what happens when it gets to its highest point. So velocity 2 will go to 0. Therefore, pressure 1 will equal pressure 2 plus rho G Y2. We're looking for pressure 1. Pressure 2 is open to atmosphere, so we know that's going to be 100,000 pascals plus rho 1,000 times G, 10 meters per second squared, times Y2. We want that 10 meters high. So P1 is going to equal 100,000 plus 1,000 times 100, or a total of 200,000 pascals. Okay, so that's the pressure that we need total. So 200,000 pascals is equal to P1, which is equal to atmospheric pressure plus rho GH. where P0 here is our atmospheric pressure, 100,000 pascals. Rho GH here is our gauge pressure. So if 200,000 is equal to 100,000 plus the gauge pressure, that means our gauge pressure must be 100,000 pascals in order to make the water fountain shoot the water 10 meters high. Let's take a look at one more, an elevated cistern problem. We've got a water cistern that's elevated 15 meters above the ground, and it feeds a pipe that terminates horizontally 5 meters above the ground as shown. With what velocity will the water leave the pipe, and how far from the end of the pipe will the water strike the ground? Well, the first thing I'm going to do is try and come up with a strategy here. I think I can use Bernoulli's principle to find the velocity of the water right here at what we'll call point 2, and then it becomes a projectile problem as to where it's going to land. If we call this our point 1, we've got a height of 15 meters here and a height of 5 meters here. To find the velocity, why don't I just bring this back, and if I call point 2 ground level for the first part of the problem, for figuring out the velocity, then the height here will be 10 meters, because that's the difference. So let's apply Bernoulli's equation and see how this is all going to look and work out. Bernoulli's equation, P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. All right, as we look at that, some simplifications we can make. P1 is open to atmosphere. P2 is open to atmosphere. They'll have the same pressure. We can subtract those out of both sides. V1 is going to be roughly 0. We can make that go away. On the right-hand side, if we're calling this the 0 height level for the first part of our problem, setting that as our 0 and the height here is 10, we can make that term go away. So we've simplified Bernoulli's equation to say that rho GY1 equals 1/2 rho V2 squared. Or, as we substitute in our values, first off, we can get rid of the rho's. GY1 equals 1/2 V2 squared, or V2 squared equals 2GY1, or V2 equals the square root of 2GY1. Notice how similar that looks. V equals square root of 2GH, the conservation of energy value we found in order to determine how fast something's moving after it's been dropped some distance. V equals square root 2GH by kinematics or by conservation of energy approach. Same idea. So V2 will be equal to the square root of 2 times G, 10 meters per second squared, times Y1, 10 meters, or square root of 200, that's about 14.1 meters per second. So our water is going to be leaving the pipe down here with the horizontal velocity of 14.1 meters per second. Now we've got ourselves a projectile problem where we've got a height of 5 meters and we need to find the horizontal distance the water travels. All right, well, let's first figure out how long that water is going to be in the air. That's a vertical kinematics problem where V initial vertically is 0. Delta Y will be 5 meters. Acceleration will be 10 meters per second squared, and we need to find the time. I would use the equation delta Y equals V initial t plus 1/2 AT squared. But again, V initial is 0, so that term goes away. T then becomes 2 delta Y over A square root, or 2 times 5 over 10 square root, or 1 second. Now I can use my horizontal kinematics to figure out how far it goes. Horizontally, the velocity is going to be a constant, 14.1 meters per second. It's going to be in the air 1 second, so delta x is just going to be velocity times time, 14.1 times 1, or 14.1 meters. Putting a couple of these concepts together in order to get a big picture solution. All right, hopefully that gets you a great start with Bernoulli's principle and Bernoulli's equation. Thanks for watching. Make it a great day, everyone.